Well, thank you for your attendance. Today I would like to talk about the high-level DNA structure. I use the high level because we're looking at the DNA structure in a scale of kilobase pairs to millions of pairs, which differs from what we learned from textbook about the double helix, or if we zoom out a little bit about nucleosome structure. It's not a simple problem, and we're still struggling to do this based on our recent technology called ChIA-PET. ChIA-PET stands for Chromatin Analysis Use PET Tag Sequencing. We developed for genome-wide identification of protein. The DNAs are fragments. For this part, they are the next part. Adapters to tens of fragments. So note here is that the DNA loop like this, and the lifted together. This we can manage the link sequence. It gives high throughput sequencing. We remove the map back the link analysis, some computing ChIA-PET. But what I do, what the ChIA-PET? Just now I mentioned that there are types of ChIA-PET. One type is self-ligation PET. A small distance, the size of the fragment, as shown here. If we self-ligation PET together, something similar to ChIA profile, we can see the peak. On the other hand, we have the ligation PET. The actually spend a longer distance from this binding site. From here, we can see is that its binding sites are still not confirmed about it could be by some randomness. Is that is this a certain interaction? We need some. Now I find some real interactions. What we do is random ligation model. Our hypothesis in a random fragment of ligation, which means suppose we have A and B. The expect of interligation PET that link and together is proportional expected number of the binding site A multiplied by the exponent of the PET ends B. So based on this random ligation model, we are able to do significance analysis. We use hypergeometric to test the significance. Moreover, we generate the random programs by permutation, which means randomly permute ends of the CHIA-PET. Based on this random model, we are able to get some FDR. Based on FDR, we say a relatively reliable list of the interactions. So next, I just briefly introduce the application of the CHIA-PET to a which is generated in cases. We generated more than 30 million, among them 4.6 million non-redundant reads are unique matches to the genome. This 4.6, 1.25 million, and the rest majority of them are interligation PET. We are able to identify the peak finding and find the binding site. We identify the binding site, and also we apply this interligation interactions. On those interactions, majority of the interactions come from the interchromosome interactions. Actually imply if there's some interactions and so the question is really mediate to the gene expression. Then we have structure to gene expression. The genes are into three types of gene: the anchor region, binding site. These regions and these anchor region. The second type group genes, which means they are in the middle of the but they a third category are not away from group. Then we do the microarray analysis. Microarrays generate time prostate. Then when we that the gene list of the anchor by those that are during for majority of those early stage, which means there are many in the whole genome. There are only a portion of them. Those that are the up to now, I just mentioned this result we published previously, and now I'm trying to come up with some new results and some of our ongoing work. There's one question we're asking ourselves. In our previous analysis, a point, which means binding site to binding site interactions that mediate some DNA looping structure. The question is there any other interaction models which are different from point interaction? I have not answered to this question, but we just have some ideas, and I would like to share with you. This is to me a interesting option from our recent data. It's not published from the growing stem. This region it's from chromosomes. Interesting to me because patterns of the left part from A but they AC it's shifted. Many and we could not looks like location it multiple loci that when we align segment, what we see that histology suggesting that this while the seems like as if what kind of structure. So this in our mind responding to this part, which to be is C is DNA pairization interaction. Pairization structure is different. Like a it's very frequent. This domain DNA fragment is a structure in our. Now, end of research of structure. Trying to summarize of interaction. Believe about the immediate by protein interactions. Second one is kind of line interaction, also DNA pairization, which means DNA is organized in parallel, which immediate series interactions in parallel. And to my point of view, this type of structure might have a more stable structure because multi-action is just like my shirt, they are left part, right part. Multiple buttons, it's firmly connected together. Remove them alone, they will be vulnerable. The last model is integration, which means we have a domain. It's just like a room. In this room, the DNAs are interacting with each other freely, but inside this room do not interact with the DNA outside. So this is another model. I have no idea about which is real, and I believe there are still a lot to be done. But I think this model may be helpful for to get out of the reconstruction of three-dimensional structure. Finally, I'd like to talk some problems. I bring problems analyze the CHIA-PET problem, which sounds to be also when talking about DNA actually about the chromatid structure for the organisms there are, and in with such problems in some group will identify the impact of two of chromatid, but often because they are using sequencing based approach, don't know where from. So this is it's still open. A second, I think this is still a in the English, and the describing this how to turn a three-dimensional model with neat computing process to dimensional strong the English. The problem to me is the stochastic itself is a molecule in the nucleus, so it's a diamond. And in the last year, the high group published a paper in describing some DNA factor model of the DNA compared to a equilibrium model, and it could be more and unfolding of during the application. That's a very good work. But there are some stabilized. Those stabilized structures mediate the and possibly can determine the self substrate. And they have the in mind. Another question, now I show the which this in G block, and this block is dimensional visualizing. In terms of the interaction, actually two-dimensional. So it's important to extend our one-dimensional to two-dimensional. This will later create the searching space, and we need to have the structure fit the inquiry from the so this is an information I will do. The CHIA-PET project was in collaboration by our groups, Eugeni's group, Ken's group, Edwin's group, and we also would like to thank this group for their constructive suggestions to data analysis. Thank you.
Thank you very much. I think we have time for some questions. So anyone that have questions, please go to the microphone.
Can I ask you two questions? When you were talking about DNA parallelization, do I understand correctly that you link it to repression? And if you do, why you do so? The second question is, how stable are these DNA parallelization events?
I don't know. We need to validate it using some wet lab. This is just a model in our mind, and wet lab validation to look at the stability of the DNA parallelization.
So, do you guys have this data available in terms of the structure, inferred from these experiments?
You are talking about we say the structural data rather than the raw data.
Exactly. Not the one you just showed, where connect to where, but
Yeah.
In terms of three-dimensional space.
And in the past, we have developed a ChIA-PET pipeline, but now we are still on the process to enrich the functionality of this ChIA-PET browser, and we are trying to make some beautiful visualization way to visualize this type of. It's on the way.
Very interesting, and I'm especially interested in your other modalities of interactions, like the line-to-line and the interdomain interactions. In the case of point-to-point interactions, it's pretty clear how to define replicate consistency. Have you thought about what replicate consistency means for these other kinds of interaction modes? In other words, how could you compare, for example, in a line-to-line predicted interaction between two different experiments, which might give you very different kinds of reads, because they might wind up in different places?
I think this is a critical question, but I think in terms of the reproducibility of the data, actually we have different biological replicates of the data. About the CTCF data, we found that this type of patterns are consistent among the biological replicates, and but we are still not confirmed that whether or not this structure is real, because just now I have talked about the prompted problem. We are not sure whether or not this is a real looping structure or it's just a shift of the prompted. So, but this is a difficult problem because the sequencing-based approach, from sequencing-based approach, we don't know where the reads come from. But anyway, to my point of view, there are always some parallelization in this case, regardless of whether or not it's a looping structure or it's just a parallelization of two chromatins.
Thank you.
So thank you very much.
Thank you.